So, we have discussed first order differential equations and the techniques that we use to solve them, and we have also discussed the idea of a system of first order differential equations. And now we will put our ideas into practice, and we will try to give a very practical chemistry example in which can be formulated as a system of first order differential equations. And the example I am going to take, it's an example similar to ones that you have seen in your chemical kinetics courses. Okay. So I'll write the problem on this side, and then we'll write the solution on the other side. So the problem statement is the following: you have a series of reactions, A going to B, which reversibly goes to C, and that gets converted to D. Okay. Now this is a set of elementary reactions, and the rate of this reaction is K1, and this is K2, the forward reaction. The backward reaction is K minus 2, and the forward reaction, this is given by K3. Okay. So these are all elementary unimolecular reactions. Okay. Now I'll just go through the statement of the entire problem, and then we'll try to work out the solution. So the first part is write as a system of coupled differential equations. And what I mean is, you write the rate equations for these for all these reactions as a system of coupled differential equations. Second one, we let y vector is a 4-component vector with 4 components, A, D. So it's a vector, it's a column vector. The 4 elements of the column vector are the concentrations of A, B, C, and D. So let y equal to this, and write the 4 coupled differential equations as a single differential equation for y. Then the next part is, you consider a trial function. So trial function, trial solution y equal to y0 e to the lambda t, okay, and identify y0 and lambda. Okay, so you try this. So try the solution in the differential equation, and you identify what y0 and lambda are related to. Okay, then the solve for K1 equal to 1, K2 equal to 2, K minus 2 equal to 1, and K4, K3 equal to 2. So you solve this problem for this for these values of k with initial conditions a at 0 equal to a0, concentration of b at 0 equal to concentration of c at time 0 equal to concentration of d at time 0 equal to 0. So, initially the value of a is a0, the value of b, c and d are all 0. Okay, so you solve and solve using these values of k. Okay. So this is what you want to solve, and as we are solving this, as we solve this this problem, you will see applications of the concepts of both linear algebra and first order differential equations. Okay, so let's go ahead and work out each of the parts. Okay, so write the system as write the following rate equations as a system of coupled differential equation. So I will just specify write rate equations. Okay. So let us go ahead and write that. Now the rate equations, assuming all these are elementary unimolecular reactions. So you can write d concentration of A by dt is equal to minus k1 times A. So the rate of this reaction is just k1 times A. Okay, so the rate of change of A with respect to time is just minus k1A. Then you can write dB dt. Now the rate of change of B is produced at a rate of k1A, B is produced at a rate of minus k2C, when B is consumed at a rate of k2B. So you can write this as k1A plus k minus 2C minus k2B. Okay. Then you can write dC by dt using similar arguments. C is produced at a rate of k2B, but it is consumed at a rate of minus k2C and k3C. So I can write k2B is the rate of production, and it is consumed at a rate of k minus 2 plus k3C. Okay. And finally D is equal to k3C. Okay. So we wrote these as a system of coupled differential equations. So we have 4 quantities A, B, C and D, okay, the concentrations of A, B, C and D, and each of them are changing with time, okay, and the differential equations for the rate of change of each of them is they are all coupled differential equations. Okay, so the rate of change of B depends on A, C, the rate of change of C depends on A, on D, and so on. So C depends on B and D depends on C. So there is some amount of coupling between these various equations. Okay. So this completes part A. Okay. So now the B part. Now here we say y is equal to A, B, D. Okay. Now we can write expressions. We can write this as dy by dt is equal to dA by dt dB so it looks very much like y, but instead of A you have dA by dt instead of b we have dB by dt, c we have dc by dt, and instead of d we have dd by dt. So, this is the vector corresponding to dy by dt. And now we can use the, because dA by dt is given by k1a, dB by dt is given by k1a plus k minus 2c minus k2b. So, you can write this whole thing in the following form. So, you can write this as minus k1 0 0 0 times a okay. So now you can say that dA by dt will be minus, so when I multiply this matrix to this vector, the I'll get a vector, the first row of the vector will be minus k1 times a, okay, and minus k1 times a is dA by dt, and that is exactly this equation. Then dB by dt I can write using the same argument, I can say there should be k1 minus k2, okay, and k minus 2 0. Okay. Then d, so that will ensure that dB by dt is k1 times a minus k2 times b plus k minus 2 times c. So, k1 times a minus k2 minus k2 times b plus k minus 2 times c. Now, dC by dt I can write as, so you have k2 times b, so there is a k2 here, and you have minus k minus 2 plus k3. C, and then it is independent of d, and for d these two are 0, and this is k3, that is 0. Okay. So, then I can write, if I call this matrix as capital K, okay, then I can write dy by dt k y, because this is simply y vector. So, dy by dt is a matrix k times y, where k is this matrix. So, this completes part B of the problem. Okay. So, we have completed, first we wrote it as a system of differential equations. Okay. So, remember that the concentration of A, B, C and D, they all change with time. So, we wrote rate equations for how they change with time, and then after that we wrote this 4 coupled differential equations, first order differential equations, as one equation, okay, for a vector, one vector for the rate of change of a vector, and since it is a first order differential equation, this involves a matrix K. Okay. So, now next in part C we want to use a trial solution, okay, y equal to y0 e to the lambda t. Okay. So, what we are going to do is we are going to substitute in this we are going to substitute for y, and we are going to see what we get. So, I'll keep erasing the top section and leave the bottom section. So, for parts, so let's go and do part C of this problem. So, part C, what we do is in this equation we substitute y equal to y0 e raised to kt. So, if I substitute that, then I get d by dt of y0 e raised to lambda t is equal to k y0 e raised to lambda t. So, all I did was wherever I had y, I replaced it by y0 e raised to lambda t. Now, remember y0 is a vector, okay, but it is independent of time. So, it can go outside this equation. So, then what you are left with is d by dt of e raised to lambda t. So, this will just give me y0 lambda e raised to lambda t. Okay, so I just take a derivative of this quantity, I just get lambda e raised to lambda t, and this is y0 vector. Okay. And here I will get k, I just get y0 e raised to lambda t. Okay. So, now e raised to lambda t is just a scalar. So, I can cancel it from both sides, and so I get the equation. So, this implies k times y0, k is a matrix multiplying a vector y0 is equal to, and I just write this in the other way, lambda is a scalar times y0. Okay. And this has exactly the form of an eigenvalue equation. Okay, so, this looks just like an eigenvalue equation. So, this implies y0 is eigen vector of k with eigenvalue lambda. Okay. So, what we have done by this method is that we have shown that if we write the differential equation in this form, okay, then our matrix k, okay, all we need to do is to find the eigenvalues and eigenvectors of k, and then we have the solution to the differential equation. Okay. So, our problem of solving a set of coupled differential equations is now reduced to finding the eigenvalues and eigenvectors of this matrix k. Okay. So, we have gone from a problem of coupled differential equations to an eigenvalues and eigenvectors problem. So, the next step will be to find the eigenvalues and eigenvectors of this matrix, and that is what we do in part D. Okay. So, in part D we want to find the eigenvalues and eigenvectors of this matrix, but what we are going to do is we are going to substitute the values for each of these coefficients. Okay. So, when we substitute that, I will just go ahead and fill it in here. So, you will get -1. So, this is k equal to -1, k1 is 1, k2 is 2, k of -2 is 1, k2 is 2, k of -2 is 1, and k3 is 2. So, 1 plus 2 gives me 3. So, we get -3 and k3 is 2. Okay. So, this is my k matrix, and according to this prescription I need to find the eigenvalues and eigenvectors of this matrix. Okay. So, if I find the eigenvalues and eigenvectors of this matrix, then I can go ahead and find the general solution to this differential equation, to this set of coupled differential equations. Okay. So, let us go ahead and try to find the eigenvalues and eigenvectors. In order to find the eigenvalues of this matrix k, so need to find, this is part D, we need to find eigenvalues and eigenvectors of k. Okay. So, we need to find eigenvalues and eigenvectors of this matrix. Okay. Now let us go and try to find out the eigenvalues and eigenvectors. So, to find out the eigenvalues, what we do is along the diagonal elements, okay, we subtract lambda along the diagonals, and we set the determinant of that matrix to 0. So, what we will do is -1 minus lambda 0 0 0 1 -2 minus lambda 1 0 0 2 lambda 0 0 0 2 minus lambda. So, we take this matrix, we take this determinant and we set it to 0. Okay, and this determinant is relatively easy to evaluate. Okay, you can go ahead and try to evaluate it. First of all, we notice that this is the this 1 minus lambda factors out. Okay, so this means this is equal to minus 1 minus lambda times this smaller determinant, that is minus 2 minus lambda 1 0 2 minus 3 minus lambda 0 and 0 2 minus lambda. Okay. So that is the that is the value of the determinant, and we can set it to 0. So if we go ahead and work out all the details, we will get the following solution. So when we set this to 0, what we will get is minus 1 minus lambda times minus 2 minus lambda times the product of these two. So I can write this as lambda plus 3. Okay, so that's the only term. This term is 0, and then you have 1 into this term is 0. So plus 2 lambda. Okay. So you expand this out, and this whole thing has to be equal to 0. So I can write this as minus 1 minus lambda, and then I notice that I can take a lambda outside. So lambda, I can take a lambda common factor outside, and then what I am left with is minus of lambda plus 2 lambda plus 3 plus 2, okay, and equal to 0. So I can write this as lambda. I can always change this minus into plus, because multiplying by minus 1 there will still give me 0. And then what I have is lambda square plus 5 lambda plus 6, okay, minus 2. So what I have is lambda square 0, and again I took a minus sign inside. Okay, so you can think as though I took this minus sign inside. So I have lambda square plus 5 lambda plus 6, and then I have a minus sign here, so that is plus 4. And if you work this out, you will get lambda plus 4 equal to 0. So this implies lambda equal to 0, minus 1 or minus 4. And this is a doubly degenerate eigenvalue, so I can write this as minus 1 minus 4. So these are the, so in general, since we had a 4 by 4 matrix, we should have 4 eigenvalues and 4 eigenvectors, but now we find that 2 of the eigenvalues are identical, and we need to find the eigenvectors next. Okay, you can go ahead and you can actually evaluate each of the 4 eigenvectors. Okay, I'll just so I'll just go ahead and give you the 4 eigenvectors. For lambda equal to 0, your y0 eigenvector y0 is given by 0 0 0 1. Okay. So corresponding to this eigenvalue, this is the eigenvector. Corresponding to this eigenvalue, corresponding to minus 4, the eigenvector is 0 1 minus 2 1 minus 2 minus 1. Okay. Now corresponding to 1, now corresponding to minus 1, this is a doubly degenerate eigenvalue. One of the eigenvectors we can generate. So one of the eigenvectors is 0 minus 1 minus 1 2, Okay, so if you put this back in the eigenvalue equation, you will get this eigenvector. Now we need to generate a second eigenvector that is independent of this eigenvector. Okay, in order to do that, in order to generate the second eigenvector corresponding to lambda equal to -1, we will use a trial solution. So we need a second eigenvector for lambda equal to -1. Okay. So we need a second eigenvector. Since this is a doubly degenerate eigenvalue, you need two linearly independent eigenvectors, and to generate that we say we use the concept from differential equations, and we say that we use y is equal to, we take exactly this. So 0 -1 -1 to e to the -1 t. So minus t into t plus a constant vector, that is u vector into e to the minus t. Okay. So I will just try to explain this. So this part is y0 e to the minus lambda is -1 t. So this is a solution to the differential equation. Now we want a second independent solution, and so what we will do is we'll take this solution, okay, multiplied by t plus a constant. Okay, so it's like when you had when you have one solution and you want to find a second linearly independent solution, then you multiply it by x. Okay, so it's in a very similar vein. We'll use this as a trial second solution. Now the only unknown here is u. Okay, so we need to determine u. Okay, so in order to determine u, we substitute this in dy by dt equal to kt. So substitute. So this is a try y equal to this, and substitute in k y. Okay, so that was our original differential equation. Now when you substitute this in that, you will get one term due to the derivative of this. So I'll just write it out. So if I substitute this, so first I am taking dy by dt. This is a constant, so I'll get okay. Then I'm taking time derivative of this quantity, so I'll have two terms. Okay, so the first term is minus t e to the minus t. Okay, and the second term is e to the minus t. Okay, when you take a derivative of this. So this is d by dt of this term. Now when I take d by dt of this term, I'll just get minus u minus t. Okay, and on the so this gives me the left hand side in this differential equation, dy by dt. Now for the right hand side, I get k. Now the first term is just k 0 e to the minus t into t, and second term is just plus k u e to the minus t. Okay. Now I can cancel each of the e to the minus t's everywhere, so I can cancel these. Okay. And also I notice that this is k times the eigenvector, okay, multiplied by t, and this is lambda, that is minus 1 multiplied by the eigenvector into t. Okay. So, these two terms will cancel, because this 0 minus 1 minus 1 2 is an eigenvector of k with eigenvalue minus 1. So, because of that these two terms will cancel. So, when you cancel the terms, what you will get is the following expression: 0 minus 1 minus 1 2 minus u is equal to k times u. So, I cancelled all the e to the minus t and all the other terms, and so what I get is exactly this. In other words, I can write this as I can take the u to the right. I can write k plus identity into u is equal to 0 minus 1 minus 1 2. And since you already know the value of k, you can write this as so if I do k plus identity, remember k had a, then I will get 0 0 0 0 1 minus 1 1 0 0 2 minus 2 0 0 0 2 1. So, this into u. So, the left hand side was, so when I take k plus identity, I will get exactly this matrix. So, this multiplied by u will give me this matrix. Okay. And you can solve this for u. Okay. So, actually the first equation is satisfied for all values of u. So you cannot determine all the coefficients uniquely. You cannot determine all the 4 coefficients of u uniquely, because this matrix has the first row as 0. So, the rank is less than 4. So, u cannot be determined uniquely. So, let us say that we choose and it turns out that we can choose one of these arbitrarily. Okay. So, let us say suppose u is equal to A, B, C, D. Okay. Then I can say that I can write this equations as the first equation is just 0 equal to 0. So, that is not really relevant. The second equation I can write as A minus B plus C equal to 0 or equal to minus 1. The third equation I can write as 2B minus 2C is equal to minus 1. And the last equation I can write as 2c plus d equal to 2. Okay. So, now this is b minus c, a plus b minus c. So, I can combine these two to give if I multiply this by 2 and add it to this, if I multiply this by 2 and add it to this, what I will get is 2a equal to minus 3, okay, implies a is equal to 1.5 minus 1.5. Okay. And then obviously this I can write as b minus c equal to 0.5 or minus 0.5. So, now we have two equations b minus c is equal to minus 0.5 and 2c plus d equal to 2. So, we have two equations and we have 3 unknowns. We have already determined A, okay, and so these two equations and 3 unknowns cannot be solved for a unique solution. So, in order to solve them, we can assume one value for any of these variables, and we will just choose a convenient value. We will choose d equal to 0. So, if I choose d equal to 0, we can see whether we can solve these two equations. This implies c equal to 1, b is equal to 0.5. Okay. So, then our u becomes 1.5, 0.5, 1, 0. So, that is my u. So, now I can write my general solution. So, y of t is equal to, so now I had 4 eigenvalues, I had 4 eigenvalues, 2 of them were the same, okay, and I generated eigenvectors corresponding to these. Okay. So, then I can write my general solution in the following form. I can write it as a linear combination of each of these eigenvalue equation, each of these eigenvectors multiplied by the corresponding eigenvalue. So, I can write C1 times, so the eigenvalue corresponding to eigenvector 0 e to the 0 t. So, lambda equal to 0 was an eigenvalue, the corresponding eigenvector was 0 0 0 1. Okay. So, I multiply it by an arbitrary constant and write it this way. Then I take another arbitrary constant and do the same for the next eigenvalue. So, the second eigenvalue was e to the minus 4 t. So, lambda equal to minus 4. The corresponding eigenvector was 0 1 minus 2 minus 1. Okay. The third and fourth were corresponding to lambda equal to minus 1. So, lambda equal to minus 1 had one solution which had an eigenvector 0 minus 1 minus 1 2 e to the minus t, okay. And last one C4, and now what we did to solve this, we assumed a form of y into t e to the or we assumed this eigenvector into e to the minus t into t plus u e to the minus t. So, if we put all that together, we will get 0 minus 1 2 into t e to the minus t plus 1.5 0.510, that is our u e to the minus t. Okay. So, this is a general solution. Now, there were 4 first order differential equations. So, we had a system of 4 coupled first order differential equation. Now, so there are 4 undetermined constants of integration, okay, but this is the most general solution of those 4 coupled first order differential equation for these values of k. Now, in order to determine these 4 constants of integration, what we will need to use are the boundary conditions or the initial conditions in this case. Okay. So, this is a general solution, and now what we want to do is to find out the values of C1, C2, C3 and C4 using the initial conditions. Okay. So, let us go ahead and do that. I will do it. Okay. So, we will try to put the initial conditions. Now, according to the initial conditions, the initial concentration of A is some constant, initial concentration of B, C and D are 0. So, if I put t equal to 0, I mean t equal to 0, this term drops out entirely. So, when t equal to 0, this will become 1, this is 1 and this is 1, this term drops out. So, when I substitute t equal to 0, I will get A0 0 0 0 is equal to, now C1 times 0. So, the first term has C1 times 0, C2 times 0, C3 times 0 and C4 times 1.5. Okay. So, I get 1.5 C4, and then I will get when I substitute here, what I will get is C1 times 0, C2 times 1, C2 times 1 minus C3. So, C2 minus C3. So what I will get here is, I need some more space. So, the second term I will get 0 from here, C2 times 1, okay, and since we put t equal to 0, this term gives me 1. So, C2 times 1, and here I will get C3 times minus 1. Here I will get C4 times, now this term will go to 0 because when t equal to 0, this whole term goes to 0. So, C4 times 0.5. So, what I will get is C2 minus C3 plus C4 by 2. Okay, C4 into 0.5. Okay. The next term, so I will get C1 times 0, C2 times minus 2, so minus 2 C2, C3 times minus 1, so minus C3, and I have C4 times 1 plus C4. Okay. And the last term will give me C1 minus C2 plus 2 C3. So, C1 C2 plus 2 C3. Okay. So, this implies C4 equal to A0 divided by 1.5. Okay. So, C4 is determined uniquely. Now, what about C1, C2 and C3? So in order to determine C1, C2 and C3, we need to substitute in here. So if we put C4 equal to A0 by 1.5, so this is A0 by 3. So we will get C2 minus C3 is equal to minus A0 by 3. Okay. And then if I do this here, minus 2 C2 minus C3 is equal to minus A0 by 1.5. And last one will give me C1 minus C2 plus 2 C3 equal to 0. Okay. And now we can solve these again. So if you just take these two, you can just let us see, subtract this from this. So what you will get is 3 C2 is equal to minus A0 by 3. Okay. Or you get C2 equal to A0 by 9. Okay. So C2 equal to A0 by 9. So let us check again. So minus 2 C2 minus C3. So there is this minus A0 by 1.5 plus A0 by 3, that is minus A0 by 3. Okay. And now you can calculate what C3 is. Equal to 4 A0 by 3. Oh, sorry, 4 A0 by 9. Okay, so we have C4, we have C2, we have C3, and now we can substitute here and we can calculate C1. So C1 is equal to, so C1 minus C2 plus 2 C3. So C1 minus, so C1 is A0 by 9 minus 2 4 A0 by 9. So A0 by 9 minus 8 A0 by 9. So that gives me minus by 9. Okay. So then you can, so now we have determined C1, C2, C3 and C4. Okay. So now we have the general solution. So the general solution we can write down now in the following form. So C4 was A0 by 1.5, C3 was 4 A0 by 9, 9, C2 was A0 by 9, and C1 was minus 7 A0 by 9 by 9. Okay. So, this is a solution of this system of differential equations that satisfies these initial conditions. Okay. So, we have gone so in this problem we have gone from this coupled kinetic equations, and we wrote it in the form of a matrix equation, an equation for a vector. Okay. Then we use this trial solution, okay, because we could write it as a d by dt of y as is equal to a matrix times y. So, therefore, we could write a trial solution of this form, and you can go ahead and you can solve this equation. What we noticed is that when we substitute this into our differential equation, what we found out is that we need to calculate eigenvalues and eigenvectors of a matrix K, okay, and we went ahead and we did that, and after applying the initial conditions we got this as the general solution. Now notice that this tells you how the concentrations of A, B, C and D, all of them change with time, and I do not need to write this e to the 0 t because e to the 0 t is 1. So, using this method we can go ahead and we can solve any system of first order differential equations. Okay. So, in the next class what we will do is we will go beyond first order differential equations, we will look at second order differential equations, and there are a whole range of problems that involve second order differential equation. We look at the general solution, we look at the particular solutions, and we'll again go through the same exercise of different ways of solving second order differential equation.